for joining me for this session. And today we're going to talk about internal life of your debuggers. So we'll see how the debuggers that we use every day in our work actually work internally, what they do. But before that, I would like to quickly introduce myself. So my name is Nataliia. I come from Ukraine, from Odessa. It's a very beautiful city on south of Ukraine, so you can see it on the picture here. I work here in the Netherlands, in Serbia, and I work as a software engineer, as a consultant. And so today I would like to tell you about how debugger architecture is, how does it look in the JVM. But before we can go to this topic, I would like to also give you a context about the JVM architecture a little bit and how the bytecode operations work. So this will give us a bit more understanding so we can have some more context to proceed to the debugger topic. And also I will tell you about the debugger that I have made in order to address some specific task. And I will also show you a little demo to see if it actually was a success and if it actually worked in the end. So let's get started. When you write any program in any language on the JVM, it can be Java program, Scala, whatever, you compile it, and when you compile it, it gets translated into the bytecode, which is basically an array of bytes, which is written in the class file. So you, for example, use Java-C for Java, and then you have the class file, and this is just bytes, so we cannot really easily see and understand what it means, but we can use the tool called JDWP, which comes as a developer tool with the JDK, and you can basically see bytecode in human-readable format. So every operation has its alias, and you can understand what it does. And I'm just showing you now a bit of Java code on the top. So this is the inside of the main method in Java. And you can see the corresponding bit of bytecode. So it's only part of the bytecode of this class. And it does exactly the same what this Java code does on the top. Now I'm curious to see how many of you have seen this bytecode before? Yeah, some people. OK, so it will be quite interesting to follow. So let's see. When we have a class file, we feed it into the JVM. And what is happening next? So inside of the JVM, there is a special component that is responsible for loading this class into the JVM, for validating if it's correct, if there are any errors, for linking some initial values, for initializing the default values. And then it puts these bits and pieces into the JVM memory. There are a lot of constant values that are also specified inside of the class file in a specific area that is called constant pool, a specific section. So class loader, there are usually several class loaders that are responsible for loading this into the JVM memory. And this is a very high-level architecture overview of JVM. So JVM is basically a specification, right? But there are many different implementations, and they can differ a little bit in each of these tiny boxes. But on the high level, it is quite similar to this. So you have a class loader. It loads your classes into the memory, and it parses and puts them in the right places. And then there is an execution engine, which is responsible for actually running your program. And usually, most of the execution engines, most of the JVMs, they have, all of them actually have interpreter, which is responsible for going every bytecode operation one by one and interpreting it at runtime. And it can start quickly, and it can start interpreting immediately, while in the meantime, there is also a just-in-time compiler that can process while it's running and see which bits and pieces are being repeated, and then it can optimize and insert already pre-compiled code, and it runs faster. So basically, interpreter and compiler work as a team together in order to make our application work. And another part of the execution engine is a garbage collector, which is responsible for collecting all the unused objects. So there are different parts of JVM memory. So method area, the first box on the left, is where all your constant values are going and all the values that describe your program itself. So it can be method names, class names, even method descriptors, for example, so the types which method accepts and returns. All these values, they are described in your class file as constants, and they're being loaded there. The heap area is for every object that is allocated in the runtime, it is put in the heap area. Method area and heap area, they are shared across all threads, but there is also a stack area in the middle, and this stack area, it has its own stack for every thread. So now we'll focus more on the stack area, because it's basically where most of the talk will be around. what's inside of this stack area. So for each thread, we have the stack of frames. And what is a frame? It's basically when you're running a method, you have some kind of state. And you have some local variables, for example. And this is your current state. And when you call another method, from this method, new frame is created and new state. You don't have access to your previous state from previous frames. A new frame is created and it's placed on top of your stack. And it's your current frame. And then when you return from this method, this current top frame will be removed from the stack. You'll end up in the previous frame. So this is your call stack. It just adds this new places where it puts the state of your current method run. And basically, if you don't have enough memory, if JVM doesn't have enough memory to put a new frame onto the stack, we know that it is a stack overflow error. OK, what's inside of the frame? As I said, it's local variables, so it's just an array that stores local variables at indexes, so there are no variable names inside of the JVM, and the variables are addressed by indices. And there is the operand stack, and it's another stack inside of each frame. So imagine you're running inside of the main method, and you're doing something, and basically any method that accepts values that you call, it will consume them from the operand stack. It cannot directly take them from local variables. So anything that you would like to provide to any method call, you first need to put it from local variables onto the operand stack. Any method call that accepts values will consume it from there, and if it returns something, it will put it back onto this stack. So this is the concept how JVM is running the program. That's why there are so many bytecode operations for this simple several lines of Java code. And now let's take a closer look at the same piece of bytecode that we have seen. And let's pretend that we are an interpreter inside of the JVM. So, and we already inside of the main method. So anything that the main method has accepted is already residing there as a local variable. So on the top, we see the local variables in the boxes, and on the left, it's an operand stack, OK? So on the local variables, the index 0 is already busy with your array of strings that you accept in the main method. Then we have first operation is iconst 0. It means if there is an integer, if there is an I on the start of the operation, it means it has to do something with integer. It means that we want to put an integer constant value equal to 0 on top of the operand stack. So this is what happens. Then next, iStore, it means that we would like to store the integer value at index 1 in the local variable array. And this operation will take the value to store from the operand stack. So it will place it over there. Then we have iLoad1, which means that we would like to load that value that is residing at index 1 in local variables back onto the operand stack. We saved it, and now we want to actually use this variable. OK, now we have I2D. So if you see, as you see in the Java code, we are dealing with adding two numbers, integer and double. And there is no bytecode operation that can add two values of different types. We have to bring them to one type. So in this case, it will be double, of course. And I2D means convert the value from the top of the stack from integer to double. And when the conversion is done, double value actually takes 2 slots. So any values are taking 1 slot except double or long. So these two are weird values that reside in 2 slots, both in a local variable array and operand stack. Next one, LDC2. So this is already referring to a constant pool. There is another section in the bytecode that is describing the constant pool. And there are references. So this is reference number 7. We already can see the hint that JDWP tool provided that this value is referencing to double value 1.5. OK. And it means that we would like to load this value. LDC is a constant value. 2 means that it takes 2 slots. And so this value will be loaded onto the stack. And then we perform the-add. It is double add. The two top values, double values from the top of the stack will be taken. There will be calculated a sum of these elements, and then the result will be placed on top of the stack again. And then we will store it onto location 2 in local variables. We will load that value back again onto the stack. We will load a zero value constant double value equal to 0 onto the stack. Then this is already where we get to condition. And the DCMPL is meant for comparing two double values. And it takes these two values, and if one is greater than another value, it will return 1 or 0, depending on which one is bigger. So it would return an integer value 1 in this case. So the next operation, if LE, is actually a conditional jump. It can take this value and know if it has to jump or not. So if LE means if the value on top is less or equal to 0, then jump to position 25, which is not in our case because it's actually 1. So we'll go to the next position. GetStatic is meant for loading some value from the static field onto the stack. So there is again a reference number 9 that specifies that this is a field called out, and it's located in the system class, and it has the print stream type. So we will load this value that is described in the constant pool. We'll load again our double value on top, and we will run invoke virtual. We specify which method we would like to invoke, reference number 15, which means that we would like to invoke println method, and it accepts, what it accepts is specified inside of the parentheses. So it's capital D. It means that it accepts a double value, and capital V outside means that it returns void. So these are the descriptors of the methods. And basically, it knows that it has to accept double, so the value under it, it will consider as the object reference of the object on which it has to invoke this method. So it consumes all of these values, and it prints something in the terminal. And if this, next, it is a goto, it's unconditional jump to position 33, which is returned from the method. And if this condition was true, we would jump to 25. We would load this static field again, and we would load some constant string value, which is other output, and we will invoke the method the same way as we did before and just proceed to the next operation and return from the method. So in order to do such simple piece of code, it needs to do a lot of loading and juggling between the variables and operand stack. So now imagine you're building some product where you need to generate the bytecode, and you would like to validate if it's actually correct. And you don't have any source code, you don't have Java, but you only have this class file, okay? So you can feed it to JVM, and if something is wrong, it will give you a very descriptive error where it will tell you which operation failed, why did it fail, what was the state of the operand stack on the moment of failure, what was the state of your local variable array at this moment. But it would be really nice to be able to do what we just did, to go line by line and see how the stack changes. Maybe you made a mistake somewhere in the middle and you don't understand how it came to this state. So it is really hard to debug, and I wasn't able to find a tool that would be able to show you operand stack and local variable array as you go and debug it, actually. So I started looking into the debugger architecture in JVM, and basically, for all debuggers, it looks like this. So on the right, you can see debuggers, which is any debuggers that you use in your normal life. It can be like anything, IntelliJ, Eclipse, JDB, whatever. If it is for Java, they usually use JDI, which is specific API. It's part of JDK, and it is really intuitive and easy to use. You can place any breakpoint and do whatever you like. So you can build your debugger already like that, just using this API. It's very easy. What does this JDI do underneath? It is sending packets that are called JDWP packets. And this is a protocol which is called JDWP protocol. It is over TCP. Your JVM can be on the different machine even. And this JDI under the hood is exchanging packets. It's exchanging packets not with just JVM, but with specific interface that JVM exposes for monitoring and debugging information, and this JVM TI. There is another way to build a debugger, which you can create a library in C, basically, specify some some configuration to JVM where your library is located, and it will hook it directly to this JVM TI interface, and then it will yeah, it will be basically running in the same process as your JVM. So this might affect your application run, so it's maybe not the best way to do it. So I decided that for my purpose, in order to be able to debug the bytecode without Java, so I cannot use JDI, I need something that will be exchanging packets with JVM instead of JDI. So I started looking into the JDWP protocol, and how does it work? So you start your JVM. This is actually, most of the debuggers work this way, right? You start your JVM, and you specify the configuration that you would like to enable the remote debugging. And then anything can connect to your application at runtime. So there is a specific string that you can send to the JVM. It's 14 bytes. It contains literally this string, JDWP handshake. And the JVM will reply back to you with the same string. And after that, the connection is established, and the debugger can do anything at runtime it wants with JVM, with your application. And I would like to make a note here that it is not something you should leave exposed in the outer world or in production, but there are so many servers that actually are sending JDWP handshake in the real world. If there are some tools that scan the internet, and you can see that. And it is, yeah, it's just something that can be only used for developer purposes, but it should never be part of your default configurations. So yeah, it's not something that you should enable on production at all, because through this protocol, not only you can debug, but you can like set any values at runtime, instantiate objects, invoke any methods, and you can even redefine the classes. So you can basically say, okay, instead of this bytecode for this method, please use this one. So do something else. You can put the breakpoints and see the passwords at runtime. So yeah, it's very scary stuff, so it should never be left as a default configuration. This is the points that I would like to make here quickly. But okay, this is very nice. So we established the connection. Now we start to exchange packets with JVM. And it can be a very, it is asynchronous, so you can send a couple of packets at JVM, and it will reply to you maybe sometime later. Maybe it will combine some responses together. And this is the basic layout of the, is the structure of the packets. So there are command packets that you send to JVM, only one case when JVM can send the command packet back to you. And usually JVM would send response packets to you. And they have very similar structure. So they both must contain header, which starts with length, so you know how many bytes you should read, how many bytes this packet takes. There is an ID of command and response should match, so you know what exactly you're getting response for. And then there is flags, which specifies if this is coming from JVM or to JVM. And there is, for command, a command set, and comment. There's two values specify what exactly you want from JVM. So there is a big documentation in Oracle docs, which specifies, okay, command set 1, then command 1, 2, 3, and many, many commands that all have different purpose. And here you can see all documentation basically on what data you should provide, because for some commands you need to provide data, and it can be very different types that you have to provide, and then you can get different reply data and different types that you have to consume back. And then you can also see which errors can occur during this command specifically. So there are there is a lot of commands that, a lot of possibilities, so implementing all of them is actually a lot of work. Okay, now coming back. So now we would like to place a breakpoint. We're creating a debugger, we're exchanging packets. We would simply like to put a breakpoint somewhere in our program, right? So what do? First, we need to make sure that our class that we're interested in is actually loaded in the JVM. So if you start JVM with this remote debugging enabled, you can also tell JVM, okay, please suspend, don't do anything, wait for debugger to connect. And when we are connected, we can request JVM to notify us about, like, start running and notify us about the event when the class is loaded. So you can get the class ID and the thread ID when this event happens. But there can be another flow. The JVM is already running for some time. You would like to attach to it and already start debugging something. And then you will need to request information about all classes that are available there. You will also get class IDs. Then you'll also need to request information about all threads. So it's just a bit different flow, but okay, let's imagine that it is suspended and we have the class ID. Now, for having this class ID, we can request all methods. We can list all methods in this class. And it will also provide us names and IDs, so we can look up the method we're interested in, because when we place a breakpoint, we do it using class method, like for specific method and for specific code index inside of this method. So once we have method ID, we can actually place the breakpoint, which is just simply asking JVM to notify you about this event of breakpoint. For JVM, this breakpoint event happens every line of code, but you need to specify when exactly you would like to be notified. I'll talk about it in a second. So when you hit the breakpoint, you would like to actually see some values of some variables, right? But it's not so easy. So there is a thing called debug information, and it contains of three things. One, so this is part of the bytecode, right? It's inside of your bytecode, you have the specific sections. One is at the start, you compile from this source code. Then there is a line number table. So for Java, for example, it is being compiled from Java. In Java C, generated this information. So mapping of Java lines to bytecode operation indices. So basically, we can do this mapping in the JDI, for example. And then there is a local variable table at the bottom, which is probably the most important part of it. So it is line number table and local variable table that are generated for each method separately. And local variable table contains the information about all local variables used in this method ever. And they specify the slot in local variable array where this variable is stored. And it specifies the type, the signature, and the name, and also where the visibility, from which index it starts and where it ends, like the length. So compiled from line number table are actually there always by default in the bytecode, but in order to get local variable table, you need to specify the debug, you need to compile it with debug mode on in Java C. But for me, these first two are not even necessary. They're there by default because when you have the stack trace, when you have exceptions, you actually have line numbers. And this information is necessary not only for debugging. But this one is only used for debugging, and without it, I'm not able to request any variable values because I need to know where the variable is located and what type it has. Otherwise, there's no way I can request the value of it. So in order to debug my bytecode that I supposedly generate, I need to also generate for each method local variable table, so I need to take in account where the visibility of each variable starts and ends, and so on. Okay, but once this is generated and JVM has this information, we can request for each method using the JDWP the variable table, and then we can see if this variable is actually available on this line of code, and we know the type, we know the index, we can request the value. If it is primitive type, it's very easy to request the value immediately, or you might get a reference for some more complicated types, and then you need to do some more requests to actually get the values, to get the values out of JVM. So JVM likes to notify about events, and you might request a couple of events, you might request a breakpoint event, you might request a step over event, and you need to specify basically the filters when you would like to be notified. This is how you do. So you please notify me about the breakpoint specifically on this line. Actually, for JVM inside, it kind of happens every line, and step over event happens every line, but you specify kind of filters. You can also ask JVM to suspend when some event happens. So this is how the step over event would work. For for us, it looks like we click on the button, step over, and then it just does one step and shows us the values, right? In reality, we need to request a step over event. We need to, when we get this event, we request the values of all variables, so we show all the values, and we also immediately need to cancel this event because otherwise we'll continue to receiving too many events, and then the JVM will also suspend on every time it catches any event. And you can also immediately have two responses together about the breakpoint and step over at the same time even. So there is a lot of events, and you should make sure that you clear them on time and that you clear the breakpoints on time. So this is also the job of the debugger, to make sure that there is no event overhead. Yeah, I already mentioned that JVM likes to combine the things together, so sometimes you'll get a notification about events, which will be a big fat response containing lots of them, so I just need to parse them carefully. And another interesting thing, you can request bytecodes for any method. You can actually, if you're making a debugger for bytecode, you can see which bytecode operation you're currently at, so this is very useful. And was it eventually a success to build a bytecode debugger? Well, yes and no, because with local variables, yes, it is nice, and I was able to debug the local variables as we do with normal debuggers. But there is no way that JVM exposes the operand stack information, and unfortunately, the only way to do it is to actually have the local state and like track. You know the descriptors, you know which operations are being called, you know which types you're dealing with, so probably you can also replicate that mechanism in your local application, but maybe it's not even worth it to do this. So my toy bytecode debugger is able to place the breakpoints and do the step over and see the values of the variables. Now I'm going to do a short demo. So this is the example Java class. Just some simple code to show you how the integers look and how the strings look. And I pasted in here the bytecode, so just for us to have it more easily available. And imagine there is no Java code at all, because we will be providing directly the class file, right? We would like to place the breakpoint, for example, in this class in method main. So we see that there is for each method there is a specific code section, and we would like to place it on line 15 after we do integer increment -1, which is actually a decrement, which is happening here. So after that, our value will be equal to 87. Let's try to place the breakpoint on line 15, right? So first of all, we start the JVM, and as I mentioned, you need to specify some config to start it with remote debugging enabled. You also suspend it, so JVM waits for you to attach, and then you can command to resume and give you the events. You specify the address where you expose it and your class file. So it is now started, and it's suspended, and it's waiting for us to continue. Now I'm going to start my debugger. So you can see I'm logging here that I received a JDWP handshake. It was a bit funny when I started building this application. I was surprised, why am I getting JDWP handshake, and then I get some extra 29 bytes. What is that? When I started parsing more events from JVM, I understood that it was actually JVM notifying me about the fact that it started. Okay, it's good to know. So now I have actually some documentation. So you can place the breakpoint, and I use a BP command. Then you specify the full name of class, fully qualified name, the name of the method, and this code line that we looked at. So I'm creating a breakpoint, but a deferred breakpoint, actually, because at this moment, none of the classes are loaded. Now we can actually run our JVM. It will then apply this request the breakpoints, and it has already hit the breakpoint and notified us about it, and it has already requested the values of the local variables. So we can see we hit line 15, The class is called this. This is the main method. This is the operation iLoad1. Is it correct? Let's take a look. So at the line 15, yes, it is iLoad1. And then we have local variables. We have an array, because we're in the main method is the array of strings that we receive. And we have a reference of it. Using this reference, we can fetch the values that are inside of the array, but it doesn't contain any. And then there is an integer value equal to 87, which is what we expected. Now let's do some. OK, why is this? OK, I cannot hide it. But I'm writing literally step. I don't know what you can see. Yeah. Maybe I should rerun the IntelliJ.
Maybe it's indexing.
OK. Oh, yeah. I was able to actually run the step, because I also cannot see what I'm typing. So I wanted to do a couple more steps to see the place where we actually have to deal with some strings. So we see that the integer value actually became greater after some time, because we are multiplying it by itself. And then if we do a couple more steps, yeah, we already can see the string. So the string has the value this and that. So yeah, in general, it kind of works. This kind of proof of concept worked for only bytecode, and there is no Java code. So this is all I wanted to show you today. If you have any questions, please ask me now, and I hope that you learned something new today and had fun. Yeah. Thank you. Yes, please.
What happens if there's no debug information available, that you compile the class without debug information in it?
Yeah, you will be able to go through the events, so you will be able to place the breakpoint. You will be literally going step by step, but you will not be able to request any values. So you'll be just going empty of step by step, and it is useless. Yeah. Yes, please.
What was the functional application of generating bytecode without Java?
So I was having a fun project where I was trying to create a programming language on the JVM. So I actually was using ASM, where I was generating the bytecode, and I wanted to see why is it failing. And it was way more complicated than these short pieces that I showed you, and it's not always easy to go through with your eyes and see why. Yeah? OK. Thank you. Please don't forget to rate my talk, and see you next time, and see you around at the conference today. Thank you.